This video is going to be about Newton's first law of motion. There are three altogether. This unit's going to cover the first and the third. You've probably heard Newton's first law expressed before. It's normally said something like, an object at rest will remain at rest unless acted on by a force, and an object in motion will remain in motion unless acted on by a force. But I don't think this really clarifies exactly what the law is talking about, so I'm going to restate it. I'm going to say it like this. If the net force on an object is zero on an axis, the acceleration is also zero on that axis, and vice versa. And if there's a non-zero net force on an axis, there's a non-zero acceleration on that axis, and vice versa. So I'm going to talk a little bit more about what that means. Looking at this first example here, we have an apple sitting on a table, and we can see that it doesn't have any acceleration in the x direction or in the y direction. Its x and y velocities are not changing, they're both remaining at zero. So if there's no acceleration on an axis, Newton's first law tells us that the net force on that axis is zero. So I'm going to take that information and put that into my force table and say, therefore, the sum of the forces in the x direction must equal zero because of Newton's first law. If there's no acceleration, there's no net force, and if there's no net force, there's no acceleration. And there's no acceleration in the y direction. It's not getting any faster or slower in the up-down direction. So that means that the net force in the y direction is also zero. So that's how we use Newton's first law to solve problems. And now that I have this information, I can use it to derive other interesting information. So here I can see that the only forces acting on the apple are the force of gravity pointing down and the normal pointing up. So I put those into my table and find that they must be equal to each other. And the way that I know that is really through Newton's first law. Without that, I wouldn't have known that the net force is equal to zero. Here's another example. Let's say that this object is not moving. If it's not moving, there's no acceleration in the x or y direction, so we can put 0 newtons as the net force and use those 0 newtons to come up with identities between these variables, between the forces, and solve for interesting new pieces of information about the forces, like this. So the way that we get that information that the net force is equal to 0 is through Newton's first law: no acceleration, no net force, no net force, no acceleration. Let's look at another example. Here, a car is driving at 65 miles per hour on the highway. And so we can ask, is this car accelerating? And it's definitely not accelerating in the y direction. It's not going up or down at all, so its y velocity is staying at 0. But it's actually not accelerating in the x direction either, because it's maintaining a constant velocity of 65 miles per hour. And acceleration is a change in velocity over time. So if the velocity is not changing, if it's staying at 65 miles per hour, that means that there's no acceleration. So that means that all the forces on this object must also balance out to make 0 in both directions. That can tell us something interesting as well. So to maintain that 65 miles per hour, obviously the normal force from the ground needs to balance out with the force of gravity. We can also see that the forward applied force from the car's engine has to balance out whatever force is pushing back against it, which in this case would just be air resistance. So this is saying that to keep a car moving at that rate, to keep it moving at 65 miles per hour, you don't have to apply some crazy force on it. You just have to balance out the air resistance. If you drive, you may have noticed that when you're on the highway, you don't have to keep your foot on the gas pedal and keep it floored the whole time to keep it at 65 miles per hour. You just need to keep it pressed down a little bit, enough to balance out the forces pushing against the car, in this case the force of air resistance. So this is a misconception that Newton's first law is made to address, and the correction to that misconception. So the misconception is that in all our everyday experiences, we need to apply force to keep objects moving, so we assume that without a force, objects naturally come to rest. So that's the misconception. Objects naturally come to rest if we're not pushing on them. So if this person pushes this box, it seems to naturally come to rest on its own. The correction here is Newton's first law tells us that if an object is slowing down, there must be a non-zero net force slowing it. If there were no forces acting on an object, it would keep its same velocity forever. So the reason why this box slows down is not because objects naturally come to rest. Newton's first law tells us that with no forces acting on them, they actually keep going and going and going forever. So the reason why this box is slowing down is because there must be some non-zero net force accelerating it. In this case, that would be the force of friction pushing back against the motion. For examples of objects that don't have any external forces on them to slow them down, a really common example is the Earth spinning on its axis. There aren't any forces on Earth that would cause it to slow down or speed up in its turning, and so because there are no forces acting on it, it just continues to spin that way forever. There's nothing pushing it around. There's nothing keeping it moving except its tendency to continue to move because of Newton's first law. So nothing keeping it moving. The only reason why it continues to turn is because there's nothing to slow it down and stop it. This leads into an important definition, the idea of inertia. Inertia means an object's tendency to keep its same velocity unless acted on by a force. So that's just a description of how objects always want to keep their same velocity and will do so unless we put a force on them. So inertia itself is not a force. That's a very common misconception. Watch out for that. Inertia is not a force. It's just a property of matter. That means the matter keeps its same velocity unless you push or pull on it. Objects with more mass have more inertia because it takes more force to change their velocity by the same amount as smaller objects. Newton's first law is often called the law of inertia because it describes objects' tendencies to stay moving at constant velocities. So that's what you need to know about Newton's first law. Most of the teaching that happens with Newton's first law stuff happens through addressing misconceptions, because Newton's first law does break some of our conceptions about the world that we're going to need to address going forward.